Hello everyone, welcome to the e-learning program of K.T.H.M. College, Nasik. I am Dr. M.K.Deore from Department of Physics, K.T.H.M. College, Nasik. Dear students, now in this lecture we are going to see the third unit, the Bragg's law in a reciprocal lattice, and the fourth unit, the Ewald constructions. Dear students, in first chapter we have seen about the concept of reciprocal lattice, and in the previous lecture we have seen about the diffraction of the X-ray from the crystals. In the diffraction of the X-ray we have seen when the X-ray gets incident on the crystalline material, then they get diffracted. Now see here in this figure, now these are the number of parallel planes and the incident X-ray get diffracted. Now but we know that in case of that the crystalline materials, the different crystalline materials having the number of set of parallel planes, having the different orientations and the different interplanar distances. It becomes very difficult to visualize such a set of parallel planes in case of the direct lattice. This problem was simplified by scientist P.P. Ewald by proposing the new concept of lattice known as the reciprocal lattice. The crystal structure generally expressed in terms of the reciprocal lattice, and also it becomes more convenient, and also it becomes very easy to express the photographs of the crystalline material in terms of the reciprocal lattice than the direct lattice. Now see here in this figure we can see that the incident X-ray gets incident on these set of parallel planes, and the X-ray get diffracted from this set of parallel planes. Now but here the diffraction of the incident is shown in a reciprocal lattice. P.P. Ewald constructed the sphere with the help of the reciprocal lattice and by using the incident wave vector, and that sphere is known as the Ewald sphere. Now in this case here, now this is the incident wave vector, and here the K dash is the diffracted wave vector. So with the help of this incident wave vector and the diffracted wave vector, the Ewald constructed the sphere, and that is known as the Ewald sphere. So the aim of the Ewald sphere is to determine which lattice planes will result in a diffracted signal for a given wavelength of the incident radiations. So now here we are going to see about the Ewald construction, or how the Ewald constructed the sphere with the help of reciprocal lattice. Now for that, consider here these are the lattice points, and on these lattice points, if the X-ray beam will be get incident on this reciprocal lattice point, then the rays will be get diffracted. Now let us consider the incident wave falling on the crystal has the wave vector say as the vector k, and the diffracted wave say as the wave vector k dash. In case of that the Bragg's diffraction condition, we have seen that the angle between the incident wave and the diffracted wave is the 2 theta. Now in the Ewald construction, with the help of the incident and the diffracted wave vector and the reciprocal lattice, Ewald constructed the sphere, and that is known as the Ewald sphere. Now let us consider the direction of the wave vector k is such that it terminates on the one of the lattice point say as A. Now let us consider O be the origin of the wave vector k. Now then draw a sphere with a radius OA with the center O, and the magnitude of the wave vector k, it should be the twice pi by lambda. We know that the magnitude of the wave vector k and the k dash are equal, then the diffracted wave vector k will also terminate on the sphere say as the point B. If the t points of the wave vector k and the wave vector k dash are joined, then by using the law of triangle of the vectors we get the vector k dash is equal to be the vector k plus vector g. Now where g is the reciprocal lattice vectors. Now in this way, by using the incident wave vector and the diffracted wave vector in a reciprocal lattice, the PP Ewald constructed the sphere known as the Ewald sphere. Then we can say that the Ewald sphere is a geometric construction used in a X-ray crystallography which demonstrates the relation between the wave vector of the incident and the diffracted X-ray beam, the diffraction angle for a given reflection, and the reciprocal lattice of the crystal. So student, you should remember how the Ewald sphere get constructed. Now here we are going to see about the Bragg's law in a reciprocal lattice. In the previous lecture, we have seen the Bragg's law in a direct lattice, that is the 2d sin theta is equal to be the n lambda. Now then here we are going to obtain the relation of the reciprocal lattice, relation of the Bragg's law in a reciprocal lattice. Now for that, Now let us consider the well collimated beam of the X-ray having the frequency nu incident on a crystalline planes of the crystal. Now let the energy of the incident X-ray beam is equal to be the h nu, where h is the Planck's constant and nu is the frequency. Now, but we know that the nu is equal to be the omega divided by the twice pi, where omega is the angular frequency, and we can write the Planck's constant in terms of the h bar. So the h is equal to be the twice by h bar. Then the energy of the incident X-ray becomes the energy of the incident X-ray beam is equal to be the h bar omega. Now similarly, let us consider the frequency of the reflected X-ray from the crystalline planes of the crystal, say as the nu dash. Therefore, the energy of the reflected X-ray beam is the h nu dash and is equal to be the h bar into the omega dash. Now in this case, when the X-ray get incident on the crystalline material, now then in such a type of diffraction of the X-ray beam from the crystalline planes, now there is the elastic type of the scattering of the X-ray. Then we know that in case of that the elastic scattering, the energy of the incident X-ray beam is equal to the energy of the reflected X-ray beam. Therefore, we can write the h bar omega is equal to the h bar omega dash. Therefore, the omega is equal to the omega dash. So as this is equation number 1. Now let us consider here the vector k and vector k dash be the wave vectors of the incident X-ray radiations and the diffracted X-ray radiation. If the space between the parallel planes is a free space, then the magnitude of the wave vector is given as the incident wave vector. Magnitude of the incident wave vector is equal to the omega divided by c, and the magnitude of the diffracted wave vector is equal to be the omega dash divided by the c. Now here c is the velocity of the X-ray in the free space. Therefore, by substituting the values of the wave vector k and the wave vector k dash, we get the relation, that is the equation number 1 becomes c into the magnitude of the k vector k is equal to the c into the magnitude of the vector k dash. Therefore, we get the magnitude of the k is equal to the magnitude of the vector k dash. So we can say that the magnitude of the incident wave vector is equal to be the magnitude of the diffracted wave vector of the X-ray beam. Now, by using the Ewald sphere, if we join the tip points of the incident wave vector and the diffracted wave vector, then these two wave vectors are related by the relation vector k dash is equal to be the vector k plus vector g. Now in this case here, the vector g is known as the reciprocal lattice vector. If we take the scalar product of the diffracted wave vector, now then it becomes the vector k, the scalar product of the vector k dash is equal to be the scalar product of the vector k plus vector g and vector k plus vector g. By solving these two brackets, we get the vector k dash square is equal to the vector k square plus vector g square plus twice vector k into the vector g. Now, but we know that the magnitude of these two wave vectors are equal. Therefore, this equation becomes the twice vector k dot vector g plus vector g square is equal to the 0. And this equation is known as the Bragg's diffraction condition in a reciprocal lattice. So, by using the Ewald sphere or by using the Ewald construction, we can obtain the Bragg's diffraction condition in case of the reciprocal lattice. So, the students, you have to remember about the Bragg's diffraction condition in case of the direct lattice, which is the 2d sin theta is equal to the n lambda, and the Bragg's diffraction condition in a reciprocal lattice, which is twice vector k dot vector g plus vector g square is equal to be 0. Now we are going to see here the Bragg's diffraction condition in a reciprocal lattice is exactly equivalent to the Bragg's diffraction condition in a direct lattice. That means here we are going to prove the Bragg's diffraction condition in a reciprocal lattice is equal to the Bragg's diffraction condition in a direct lattice. Now for that, you have to draw the Ewald sphere in a reciprocal lattice point. Now consider here the incident X-ray beam incident in the reciprocal lattice. It gets diffracted along the direction of the OB. Now then, by joining the T points of the wave vector, incident wave vector k and the diffracted wave vector k dash, then from this geometry of the figure, that is from the Ewald sphere, we can say that the side OA is concurrent with the side OB. Therefore, the triangle OAB is the isosceles triangle. Now let us consider the angle OAB is equal to the angle OBA, say as the phi. Now in triangle OAB, by taking the addition of these three angles, that is the 2 theta plus phi, that is the 2 theta plus 2 phi is equal to the pi. Now express it in terms of the phi. So we get the phi is equal to the pi by 2 minus theta. Now the angle between the positive direction of the incident wave vector k and the reciprocal lattice vector g, say as a psi. Therefore, we can write the psi is equal to be pi minus psi by substituting the value of this phi. So we can write the pi minus in bracket pi by 2 minus theta. Therefore, we get the psi is equal to be pi by 2 plus theta. Now from this Ewald construction, if we take the scalar product of the incident wave vector k and the reciprocal lattice vector g, now then the scalar product of the vector k dot vector g is equal to the kg cos of psi by substituting the value of the psi here. So the kg cos of pi by 2 plus theta, but we know that the cos of pi by 2 plus theta is equal to minus sin theta. So we get the vector k dot vector g is equal to minus kg sin theta. We know the Bragg's diffraction condition in a reciprocal lattice, that is the twice vector k dot vector g plus vector g square is equal to the 0. Therefore, we can write the above equation minus twice kg sin theta plus g square is equal to the 0. By rearranging the terms, twice kg sin theta is equal to the g square. So we can write the g is equal to the 2k sin theta. Now say as this is equation number 1. Now the reciprocal lattice vector g can be expressed as g is equal to the n times the twice pi divided by the d. Now here d is the interplanar distance and the n is the integer. Therefore, by equating these two equations, equation number 1 and equation number 2, we get the n into the twice pi by d is equal to the 2k sin theta. But we know that the incident wave vector can be expressed in terms of k is equal to the twice pi divided by the lambda. By substituting this value of the k in this equation, then we get the n lambda 8 is equal to the 2d sin theta. And this is the Bragg's diffraction condition in a direct lattice. That means here we can obtain the Bragg's diffraction condition in a direct lattice by using the Ewald sphere and the reciprocal lattice. And hence we can say that the Bragg's diffraction condition in a reciprocal lattice is exactly equivalent to the Bragg's diffraction condition in a direct lattice.